then we solved those examples, and now we're going to go ahead and then see more stuff. Then the first scenario that we looked at was the dropping an object, kind of, right? So when it's dropped, its initial velocity is just 0. Now, what if the object is thrown in the downward direction? What's going to happen? Then, yeah, definitely. Then now your velocity is not 0. Your initial velocity is not going to be 0. Okay. So your initial velocity is not going to be 0. This guy is not going to be 0 if there's a throwing velocity in the downward direction. Okay. All right. So then, how does the distance vary? We already saw this kind of information earlier, and then at the same time, your velocity is not going to be 0, and then you'll be using the whole distance formula, like the way you see it here. Okay. We saw how the distance varies for a time 0, and so on and so forth. Okay. So in your textbook, there's a problem that involves throwing down an object, okay, which is E5. Then I'll go ahead and then solve that for you. Then the problem states, the problem states that on my textbook, it's page 57. E5 is located on page 57. Okay. Now the very first that we saw was when the object was dropped. Dropped or released. Now thrown downward. Okay. So when that happens, then your initial velocity is not 0, is not equal to 0. So the initial velocity now is not 0. So then E5 states the following. Let's list out our given parameters. The way I solve problems is given required solution. Why I strictly follow that step? If I list all my given parameters while I'm reading the problem, then I don't have to go back and forth to pick up a parameter or to understand what is happening. Okay. So rather, I just on the way I'm reading it, I list out my given parameters. The problem states a ball is thrown downward with an initial velocity of 14 meters per second. Using the approximate value of g, what is the velocity of the ball 3 seconds after it is released? So you have initial velocity of the ball, which is 14 meters per second. And then what else it says? What is the velocity after 3 seconds? Then time is equal to 3 seconds. Okay, 3 sec. Then required after 3 seconds. In other words, you're asked to find the final velocity. Okay. Then again, our assumption is downward g as positive. Okay. Downward in general, downward positive, you can say that. Then your v final, which equation will you want to use? Will be the initial plus acceleration times t. You will be using this formula. right? Because look at your given parameters. Your gravity is already given. Gravity doesn't change whether you throw the object upwards, whether you throw the object downwards, or you release the object. Once it left your hand, the object's motion is dictated by gravity. That means it experiences 9.8 or 10 meters per second squared. It doesn't matter because the Earth doesn't discriminate. Like once the object left your hand, that's it. The motion is going to be dictated. I mean, the Earth is not like some kind of object that says like, oh, you are moving in the upward direction, now I'm going to pull you with this much. Oh, now you're going in the downward direction, oh, I'm going to pull you with this much. No, that doesn't work. Nature doesn't work that way. If it just like pulls you 9.8 when you are falling, it's going to pull you down when you are moving up. It's going to pull you down when you are free falling as well. Okay, in all circumstances, it's that 10 meters per second square acceleration. Okay. So therefore, now your v final will be v initial. In this particular problem, we have an initial velocity meter per second plus your acceleration again 10 meters per second squared. Then your time is 3 seconds. Okay, so one of the seconds will eliminate with one of the seconds. You will have meter per second again, okay, on the second term of the right hand side. So your v final will be 14 meter per second plus 30 meter per second. 30 is 10 times 3. Everything is in meter per second. So therefore, your final velocity will be 44 meter per second. Okay, 44 meter per second. Okay, that's your final velocity. That's how you approach it. That's how you solve the problem. Okay. The only difference between this problem and the previous problem would be like, if there's no any initial velocity. If the object is dropped, then okay. So now we looked at like when the object is thrown downward. Kind of approach. Then now we solved it. Now what if you throw the object in the upward direction? That's one thing. So when that happens, like the object is going to have two kinds of motion, like when it goes up and then when it comes down, and that kind of scenario. That kind of scenario. So then, but if you see it the ball, especially when it's moving in the upward direction, the ball, or a ball or a stone or a rock, when it's moving in the upward direction, right, it slows down. Then in that circumstance, like you will be somehow forced to use maybe a negative 10 meters per second squared. Okay. It's going to be negative 10 meters per second squared. You cannot use the same thing because when it's like moving in the downward direction, we were saying down was positive. Okay, because I understand like why the text is trying to move it that way. Like when it's moving up, it's negative 10. It's coming down, it's positive 10 kind of thing. But if it is like for a college physics or a university physics level, believe me, I would have approached the problem differently. Instead of changing the acceleration every now and then, I would stick with changing the velocity. changing the direction of the velocity. When the velocity is up, positive. When the velocity is down, negative. That kind of approach. But let's keep it simple, as your textbook uses it. When it's moving in the acceleration in the upward direction, because it's slowing down, then it uses an acceleration of -10. As I said, if it were a physics, or a college physics, or a university level physics, would have used gravity -10 all the time, whether the object is moving up, whether the object is moving down, would. Okay, but for now, just for this class, let's just go ahead, and then, since the ball is slowing down, text encourages to use -10. See here. Okay. Now, I want all of you to answer this question for me. This is like a very interesting kind of question. Everybody likes to ask it. When you throw an object, it goes up, and then it reaches at the top, the maximum height, right? Then it comes back down, right? So that's how it is. That's how nature treats things. Like, throw an object in the upward direction, it goes up the whole way up, and then it's gonna come back down. My question for you is, like, as you can see it in the slide, at the top of the path, that means really right here. What would be the velocity of the ball? Can someone tell me? Write your answers in the forum. Zero, 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 zero. Very good. -20. 0. Okay. Yeah. An object can only change its direction, right? An object will only change its direction. It has to stop somehow, right? So you can imagine yourself like you're walking in the left direction or in the right direction, and then you're walking like this in this direction. And then if you want to return and move in this direction, what will you do? You can do it as fast as you can, but there will be an instant of moment that you will stop to change your direction. The same is true with the ball. It's going to go up, 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 up. When it reaches to a maximum height, it will stop for a moment. Its velocity is going to be 0 at the highest point. But its acceleration remains gravity. This is a classic physics question. Like, everybody likes to ask you this. Like, you throw an object, it goes the whole way up to the highest point, and then what is the acceleration of the ball right at the highest point? It's the same, 9.8 or 10. Okay, since it's reversing its direction, you may assume it's -10 because it was moving up in the upward direction. But there is acceleration right up there, but there is no velocity. Okay, why acceleration is there but no velocity? Because that's an instant. Still, the motion is in a continuum. Motion is still, it's uninterrupted motion. It's continuing. but at certain instant of like in that diagram, as you can see, like it starts with 10-20 meters per second. Since like, you know, any object that you throw, when it moves in the upward direction, you know, it's losing its speed, right? It goes up, goes up, goes up, goes up, stop, and then it starts to come down, right? Then its speed starts from 0 and then increases. After 1 second 10, after 2 seconds 20, after 3 seconds 40, 30, after 4 seconds 40, and so on and so forth. It will increase with that same rate that we know. Okay. So that's a classic physics question, like what is the ball's and its velocity is 0, whereas its acceleration remains the same, which is, yeah. Okay. So if the object is thrown in the upward direction, then something else that you need to remember is a free fall motion is symmetrical motion. How? If you throw the object at 20 meters per second, like as you can see in the diagram, if the motion starts at 20 meters per second in the upward direction, it will come back with 20 meters per second. See? Sometimes physics is amazing. You can test it, like, you know, you can test it yourself. Like you throw a certain object like with a smaller speed, with 5 meters per second. If it is a rock, then when it comes back down, like it's going to come back with same 5 meters per second. If you throw that same rock with 30 meters per second, which is significantly high, when it comes back, it's going to shoot down with that same amount of speed, right? You have to run away from this, otherwise, it will, you know, it will definitely like it's gonna come with lots of energy. We'll talk about the, you know, the energy contents and all that later, but the idea is like, you know, it starts with 30 meters per second. It will come back with 30 meters per second. Okay, so at the same height, it has to be at the same spot, by the way. So if you look at in this diagram, at this point it's 15 meters per second. When it comes back, it is also 15 meters per second. I mean, actually it says 10 meters per second. The other thing that it makes it symmetrical is like if the ball takes 2 seconds to go up, and then it takes how many seconds to come back? The same amount of time. Okay. If it takes 2 seconds to climb up, it will be back in 2 seconds after it reached the highest point. Okay, so that's why like we call it like free fall motion. It's a symmetrical motion, usually like if it is thrown upward and so on and so forth. Okay. Then a projectile motion, you know, it's something that probably worth mentioning. A projectile motion is a type of motion that you throw an object, let's say in the horizontal direction, or like, you know, baseball players kind of throwing a ball. Okay, so in a baseball game, like when you throw the ball, right, the ball doesn't go straight, right? It has some kind of, follows something like this. Tennis playing, when you're playing tennis, it also follows some kind of path like this. So if there is, so far what we were saying is like the ball dropped, the ball thrown downward, the ball thrown in the upward direction. Okay. But what if the ball has like some kind of both horizontal component, especially like in the horizontal? Okay. So what if when you throw the ball, what if you make it like something to have a little bit of horizontal, I don't know, in physics, component. We call it component. So it's like baseball player, or if you are standing at the top of a cliff and then you throw the ball in that direction. Okay. Once it leaves your hand, it's dictated by gravity once again. Okay. You know, you can do lots of calculations and things like that, but I don't want to focus on many of those things because we're not going to do a lot of calculation and so on and so forth. But something I would like to mention is here, like if you see an object, so if you can see this animation in the slide, you will learn something about the velocity. Let's assume that like certain object is thrown with an initial velocity of 100 meters per second in the horizontal direction, like that, with 100 meters per second. If you throw this object with 100 meters per second in the horizontal direction, it's just only in the horizontal direction, what will happen is like it's going to have, at every point while it's falling, it's going to have that 100 meters per second of component in the horizontal direction. So now when you talk about a projectile motion, the motion is not only moving up and down, it's also moving along the horizontal direction. It's also experiencing distance in the x direction or in the horizontal direction. So when that happens, like its speed will remain the same as 100 meters per second. Okay, but in this direction, in the y direction, while it's moving in the horizontal direction, it's also falling. It's falling this distance. Look, it's falling this much distance, right? But falling is what? Falling is dictated by gravity. That means when this object is falling, its motion towards the earth is dictated by gravity. Its motion in this direction, in the horizontal direction, is dictated by the initial velocity that you give it, by the initial velocity. Okay, see, and that initial velocity just remains constant throughout the trip. Okay, so just to see the animation, look at how the numbers change. Vx is the velocity in the x direction, Vy is the velocity, you know, at which it's falling. So in 12 seconds, like, you know, every second in the y direction, its velocity. So that means you may say, like, how come an object has like a velocity in the x and a velocity in the y direction? Yes, it has, because the object is not moving just only in the falling direction, or the object is not only moving in the horizontal direction. It's experiencing both of them. Okay, it's experiencing both. Okay, so that's what a projectile motion means. Okay, so having said that, like, I want you to look at this diagram, and this diagram was or this picture was taken like with like in a laboratory with a high-speed camera. What happened is they dropped an object from a certain height, and the red ball was dropped like this, just whoop, let it drop, whereas the yellow ball was thrown like this. Which object do you think will hit the ground first? So this is the yellow. I'm going to represent it as Y. And this is the red. This is how they were released at the same time. Which one do you think will hit the ground first? Anyone? The yellow. Which one will hit the ground first? The same? Red. Same. Both. Okay. If you are answering both at the same time, then you're correct. Why? Look, what we said is, in the previous slide I mentioned something, if you remember, like if you throw this object in perfectly horizontal direction, with any velocity it is, its horizontal direction or its horizontal motion is dictated by how much velocity you applied. Right? If you start its motion by 10 meters per second, it will continue in the x direction with 10 meters per second. But how about its y direction motion? Its y directional motion is going to be dictated by the Earth's gravity. In this particular problem, the yellow ball has an initial velocity in the y direction, or in the downward direction, equal to 0, because the ball was just perfectly thrown in the horizontal direction. That means its initial velocity in the y direction is 0. But still, its motion, its falling motion in this direction is going to be dictated by gravity. When you look at the red one, to start with, it didn't have any kind of horizontal speed or initial velocity. What it had is like just an initial velocity in the vertical direction equal to 0. So there is no difference in the vertical direction. The red and the yellow ball experience the same thing. The only difference is the red ball, it didn't move in any direction, whereas the yellow ball, it traveled this much distance in the horizontal direction. So that's why it says, like at the beginning, you ignore air resistance and so on and so forth. That means if there is no any air resistance, the yellow and the red ball will hit the ground at the same time. But if there is air resistance, maybe the yellow ball will experience a lot of air resistance because it's traveling a longer distance in the horizontal direction. But in the vertical, the yellow ball is falling, the red ball is also falling. Both scenarios are falling. And both scenarios had initial velocity of 0 in the vertical direction, or in the falling direction. Okay, so therefore both of them will hit the ground at the same time. There is a problem E15 that involves, like, if an object rolls off at a certain height. I mean, I don't expect this problem to show up in your quizzes or exams, but for the sake of it, like I just like to solve it for the sake of completion and understanding the material. So E15, it states the following. A ball rolls off a platform that is 3 meters above the ground. The ball's horizontal velocity as it leaves the platform is 5 meters per second. How much time does it take for the ball to hit the ground? So the question is like this. So it rolled off a height of 3 meters. Okay, and it says the ball rolled off that table. It means it had a perfect initial velocity in the x direction. So you can call this, like, horizontal. In the horizontal, it had a perfect 5 meters per second. But how much would be its velocity in the vertical direction? Can't say anything. Sorry. So the ball rolled off. So when it rolls off, like, you can roll off like a coin, for instance, on your table. It has like a perfect horizontal one, but in the vertical direction, because you didn't throw it in the vertical direction. it just rolled off by itself off the table. And if the table is like on a perfectly flat surface, then it just moves in the horizontal direction, but in the vertical direction it doesn't have anything. Yes, it's the same page 56. Okay. So now the very first question is asking you, like, I like to sketch this one because, you know, so that you may have some understanding of what is happening. So the ball is going to travel like this, right? It's going to fall like this. So it's going to be a certain distance, like, you know, I'm going to represent this as x, certain distance that it's moving from the table. It's not going to drop straight down on to the bottom of the table right here. No, that's not going to happen. Okay. So now here are the given parameters. Now the question says, how much time does it take for the ball to hit the ground? Then how much time? Okay, let me use mine. So this object is a free fall object. I mean, if you consider it like only the horizontal one. Yaozan gave me an answer. All right, let's see. Okay, so what you can do is, like, the two motions are independent. Okay, so vertical motion and horizontal, because the object is falling at the same time it's moving away from the feet of the table. So the vertical and the horizontal motions are independent. Because one is dictated by Earth's gravity, the other one is dictated by the initial velocity. Okay, independent. So from what you know, there's a formula which says d is equal to v initial times t plus half times acceleration t squared. You use this for the part of the motion that has acceleration, and of course that motion is the vertical. Okay, so now your d is 3. Your initial velocity in the vertical is 0 times t, because the ball just rolled off the table. Nobody threw it in the downward direction. It just rolled off the table by itself. And plus half times acceleration is 10. Time, you don't know time. So what you will have is like 3 equals half times 10 times t squared. You need to isolate t in this particular problem. What do? So you need to multiply this guy by 2 so that this can cancel out, and you need to divide this guy by 10. But if I do that, I need to do the same thing on the right, on the left side. Okay, so I need to do the same thing. I need to multiply this by 2 and divide it by 10. Then what will be this? This will be 2 times 3 is 6. 6 divided by 10 is 0.6. Is equal to t squared. So this is 0.6 is not t. This is t squared. Okay. So what do? To get the value of t? Square root both. Because you have a t squared on that side. You need to isolate it. Okay. Then square root it. Square root, just, you know, apply your calculator. You use your calculator to find it. Okay. So then, you know, this will be t. The square root of t squared is t, and the square root of 0.6 is going to be 0.6, you can try it. It's going to be plus or minus 0.77 seconds, right? I don't know if you remember from your algebra, because 0.77 squared will give you 0.6, negative 0.77 squared will give you 0.6. I'm saying it for the sake of completion, because time cannot be negative, right? You pick the positive. So therefore your time is going to be 0.77 seconds. All right, so it was already answered. Thank you very much, guys. Okay, that was awesome. So that's it. That's how you find it. It's not really that hard. If you look at the B part of the problem, it says how far from the base of the platform or the table that the ball hit the ground. Like part B is asking you like how much is x, how much is the value of x. Well, you can find x, but remember, the horizontal motion is not dictated by acceleration. That's what we were saying, guys. X, or this, how far from the bottom of the table this object is going to fall, this distance, is not dictated by gravity. It's dictated by the initial velocity. And I mentioned that like the velocity is constant throughout in the horizontal. If it starts with 5, it's still going 5. When it hits the ground, still has that 5 meters per second in the horizontal direction. So therefore, if distance, how do you find distance? If it is constant velocity, I put it as x, you can put it as d if you wish, but you will use speed times time. Remember that little formula, speed times time? And you already know the speed is 5, which is given, multiplied by 0.77. Everything is in SI units, then you know, your x will be, or your distance will be in meter. So 5 times 5, 35, 38. So it's going to be 3.85 meter. That's what the answer is. Okay. All right. Yao Zong, yeah. Thank you. That was the right answer. Okay. So this is what you do, like for instance if it involves a projectile motion. Okay, so in a projectile motion the object is moving in the x direction or in the vertical direction, at the same time it's moving in the horizontal direction. That means if you coin next time it if it rolls off a table, and if you drop it straight from your hand, they don't experience the same kind of motion. The one that rolls off, it's dropping, but at the same time it's moving in the horizontal direction. Okay. All right. Excellent. So yeah, you guys are great. I mean, I see like just this thing is making sense for you guys. Awesome. And yeah, just try to sit and look at the video again and try to solve more problems or something like that. Just sometimes it's for the sake of it, for the fun. You do those kind of simple physics, mathematics questions. They do really help you somehow. In terms of understanding things. Okay, kind of outside of this, but is it possible to have Earth's gravitational pull stronger in certain locations to cause something to fall farther than objects normally fall faster than their initial velocity? Definitely. You mean in the Leland? Like, I'm trying to understand the question. Like once an object you know, so we mentioned earlier, if you remember, yeah, I'll try to revise it again. If the object has an initial velocity of 0, then after 1 second its velocity is going to be 10 meters per second. After 2 seconds its velocity is going to be 20 meters per second. So 20 meters per second is faster than 10, and the initial velocity is then 30 meters per second. If you do the same kind of experiment, but if you give it an initial velocity, that means you're throwing down the object. So after 1 second is not going to be the same as the falling object, the dropped object, because we gave it an additional 10. So in this case, the velocity after 1 second is going to be 20, because you already gave it that 10 thing at the beginning. Then after 2 seconds, it's going to gain 10 plus 20, which is 30. After 3 seconds, v is going to be, the 30 that you have from here, and then plus the 10 again. Or let me keep the same order, just to avoid confusion. The 10 plus 30 will be 40. So this is time at 1 second, time at 2 seconds, time at 3 seconds. Okay, units are important. Okay, so therefore, yes, once it left your hand, then of course the object moves faster than its initial velocity. I mean, anywhere on the surface of the Earth that happens. Okay. Any other question? Anyone? I encourage you to solve those questions. Those are you can consider them as part of your revision for chapter 3. I mean, okay. Any other question? So we have about, let's say, another 10 minutes or something, so probably we can go ahead and try to start chapter 4.